Who uses flow simulation? Well, this is a breakdown of typical customers buying flow simulation. In addition to typical aero, defense, and transport, and medical and valve industries, there's a large percentage of users in electronics, and that would be for thermal management. Because with flow analysis, it's the ideal tool for doing thermal management, since we can capture radiation and convection effects much more easily than you would in an FEA environment. Why do we want to simulate? Anytime that we can learn more about our design early on, the cost of change is much lower. We get to an optimized design much faster and less expensively when we have tools that can give us upfront knowledge about our systems. Today, specifically, we're going to look at a couple different applications. One is going to be CV calculations in a valve, which is actually a very common request, so I want to cover that. Next, we're going to look at a heat exchanger application, and this would be for a glue applicator. And we're going to be looking at our material delivery temperatures. So we have a glue that we want to keep at a consistent temperature. We can also look at things like operator comfort near the equipment. And this is an internal and an external flow problem with multiple fluids. Next, we're going to get into an external flow analysis of a LED system, looking at heat sink comparisons. Next, we are going to explore some of the capabilities in the electronics cooling module that allow us to create a more accurate analysis of electronic systems, PC boards and circuits, thermoelectric coolers, heat pipes, etc. And lastly, we're going to show how we can transfer pressure as well as temperature to structural analysis. So, we discussed very briefly, why simulate? Well, early on in an analysis, let's just compare what I call a napkin sketch ROI. A typical physical prototype, our first prototype, $2,000 is pretty cheap, and $800 in labor cost to do an evaluation. And, with each iteration that goes by, we can very quickly, time adds up, and so does cost. But if we just compare this to a virtual analysis or virtual testing, we can see that we can drop our time and our costs by orders of magnitude. So let's get into the CV calculation for a ball valve. And what is a CV coefficient? It's essentially flow divided by pressure drop. And specifically, the units are gallons per minute per PSI of pressure. So it's how efficient is my valve. And we're going to start out with our simple model here of a ball valve. And to begin a flow analysis, the first thing that we want to do is load in the flow simulation add-in. So once the flow simulation add-in is loaded, we see that we get a flow command manager with a wizard. So starting from left to right, the features that we're going to need to set up our analysis, run it, and then review our results. And then we're also going to get a flow feature manager. And with the ball valve, it's really quite a simple setup. We're just going to drive the flow with an inlet mass flow and then push up against an environmental pressure. And from there, we're going to evaluate goals. And in this case, we're going to create a CV equation so that we can get a flow efficiency calculation. And then we're also going to show that we can very easily copy this over to another configuration. You see here that we have the ball valve at 30 degrees and the ball valve at 15 degrees. So let's start from scratch very quickly here. We go to the flow simulation command manager and we start up our wizard. and it asks us what configuration do we want to use. I can copy it across config, so I'll just leave it in the 15-degree configuration. And we choose our units, and we can mix and match, but I have my CV equation worked out so that I'm going to stick with SI units. And in this case, this is an internal analysis, so all the flow is within manifold geometry. And we're not going to be doing heat calculations, so we don't need to choose that information. The next phase is that we pick our liquids in the model, or fluids for that matter. And we're going to choose water. But as you see, we have a large database of predefined liquids, non-Newtonian fluids such as oils. We can also do compressible liquids, real gases, and steam. If we need to add a liquid or any fluid for that matter, we can say new, and this brings up our flow engineering database. And it's just as simple as taking, say, an existing property, copying that, pasting, and then we can begin to manipulate our tables and curves. So for this example, we're dealing with the gas, so we have dynamic viscosities, specific heat, thermal conductivity, etc. For this model, we're going to choose water as our default liquid. We'll leave cavitation off, and we can let the solver decide whether we're dealing with laminar or turbulent flow. Next, we can pick wall thermal conditions and wall roughness. Since this is a pure flow calculation, we'll just leave it an adiabatic wall. No heat is entering or leaving the system. And lastly, we choose our initial conditions and our mesh settings. So we've got an extremely intelligent mesher. We have algorithms that we can enable for narrow channel refinement, and we can also define minimum gap sizes in the model so that the mesher will know that it needs to reconcile gaps up to that dimension or down to that dimension, and won't mesh as finely gaps smaller than this, so that we can keep our model sizes very manageable. And once we finish the wizard, we get our base flow model in the feature manager for flow simulation. And flow, like our other simulation tools, are inputs on the top, outputs on the bottom. And I need to start defining boundary conditions to drive the flow of this model. So I'll use a section view so it's easy to get to my faces that I want to select. And the first thing that we'll notice is there's a little rectangle here, and so flow is already kind of determined. All right, this is the size of the model, and this is where I expect the fluids to be. And now I want to enable my boundary conditions. So with the right mouse button in the feature manager, I can click on the boundary conditions, and we have mass flows, volume flows, velocities. In this case, I'm going to drive the model with an inlet flow rate. And all I need to do is pick the face where I want the fluid to enter the system. Now I need to push this flow up against the pressure. So I can also, from the boundary conditions dialog, we can switch to pressures. And I'll push this up against environmental pressure. We're going to be looking at a comparative delta pressure to do our CV calculation. So now we are driving the flow model, and before we get much further, we want to make sure that flow is happy with the geometry. So when we go up into the command manager, we have a check geometry capability, which is going to look at the CAD model and make sure that we're happy, that we don't have any strange gaps or contacts. And if we did, it would help point them out for us. So we see that flow correctly predicted what the fluid volume would be in this model, so we can begin with the next steps in setting up the flow run. The second phase, after setting up our boundary conditions for this model, is to determine the goals of the simulation. And so we have global goals, and this is all information that the solver is going to use to help come to convergence, and it's all information that we can look at during the solution and extract very easily as result sets. things like forces on faces, global velocities, densities, and maximum velocities, etc. But for this problem, I'm going to use surface goals on the inlet and outlet faces. And I want to create a goal for each surface that I've selected. We're going to look at average static pressure and volume flow rate so that we can create our CV calculation, which is flow rate for a given pressure drop. So I'll just do a quick rename. So with these goals that we've created that are going to give us our inlet and outlet pressures and our flow rates, I can begin to create equations. So I want a pressure in minus pressure out. This will give me my delta pressure. And now I can build the CV equation. So given the unit system I'm in, I have a couple correction coefficients so that we get gallons per hour per PSI. I choose my volume flow rate. Divided by my static pressure drop. And I need to divide that by 1,000. And then take the square root. There we go. And so now we have our equation goal that's going to calculate our CV, our flow coefficient. The next phase is to solve the model. And I have two versions of this model, and you can see for 2013, the way we organize our projects is very nice. We have two configurations of the model, and then we see the sub-projects under each configuration. Right now, I just created this new analysis under the 15-degree study. So let's activate the existing model where I already have a result set. And we can load up our results. So one of the first things that people think of when they think of flow analysis are flow trajectories. It's kind of one of the sexier plots, and it can tell you a lot about the quality of the flow. In addition, the contours of the flow trajectory are meaningful. As we see here, these contours represent pressure, and they're shown as a simple trajectory. Anything in a flow analysis, I can just clone that and redefine it if I want to manipulate it. And I can change this to spheres. We see that we're getting a little bit of recirculation here as we exit the ball valve. And we might want to look at this flow in terms of a cut plot. And cut plots in flow analysis are just like cutting a section in a drawing. We pick a plane and an offset, and what are we interested in looking at? And in this case, well, we're going to look at pressure with velocity vectors overlaid. So it's one thing to visualize the flow, but if we want numerical data out, anything that we've created as a goal can very easily be plotted out, either sent to Excel, or we can view a summary chart within flow analysis. So we get a summary of our average goals that we've selected in our goal plot, and we can also look at them in XY format. In this case, I want to be able to compare my flow coefficients across my different models. So in this one SOLIDWORKS model, we have two configurations, and I want to see how the CV values for 15 degrees might compare to 30 degrees. So I can go into SOLIDWORKS, the comparison capability in Flow, and select my two projects that I've run and tell it I want to compare my goal plots. This loads up the results for each study. And as we'd expect, the flow rate for a given pressure drop is going to be much higher for the ball valve that's only at 15 degrees versus the 30 degrees. And we get a nice summary of all the other goals that we requested, maximum velocities, and then we can also view in a comparative chart format. And this actually can be very handy if you've got a lot of projects in one model and maybe you haven't run one quite to completion yet. Being able to look at the XY plots, we can see that both of these studies have come to steady state. Now, we've looked at data in an XY format from goals that we've created ahead of time, but we can also create XY plots. And one thing I really do like about FlowSim is that, for example, I can create sketches after the analysis has been run. And I can reuse this sketch to create an XY plot. So it's going to give me any parameter that I ask, for example, pressure along the distance of this sketch. That is the general process. We start with our wizard. We get our basic flow model set up. We apply our boundary conditions. We define the goals of the simulation. And then we can review our results with cut plots, surface plots, and flow trajectories. And now if we want to clone this project, I can just copy it or clone it, and then I can copy it to another configuration. So we built this on 15 degrees, and I could very easily select as many configurations of the model that I would like to apply this set of boundary conditions.